Hey, and welcome to my Physics 2211 lab. Frick, I have to set up a timer, otherwise I'm going to talk for too long. Okay, so the introduction. So the objective of this lab was to demonstrate the principles of Newton's second law by comparing the the computational model of an object to the object's actual motion. The principle behind this lab is that Newton's second law tells us that the net force on an object is equal to its change in momentum over the time it took to change. A derivation of this formula also tells us that V final equals V initial plus F net divided by m times t, where F net divided by m is acceleration and t is the time it accelerated. And this is also known as our velocity update formula. So that's where we get our velocity update formula from, Newton's second law. So at the end of this lab, we're going to see that the velocity of an object, of the object we experimented on, changed, indicating that there was some force applied to it. We'll get there later. So to do this lab, we compared a computational model of an object with the actual object. So we recorded an object rolling on a table, and we assumed that we didn't do anything to it. We assumed there were no external forces applying on it. We uploaded that video to Tracker, and we created frame-by-frame tracking on it. We graphed the data we got from Tracker into a line graph. Then we went into GlowScript and we created a computational model of the object rolling in GlowScript. We graphed the data obtained from the computational model into a line graph. So we have two line graphs, one of a computational model and one of a real experimental model, which means we have an easy way to compare those two things. And then when we compared, we were able to make inferences about the experiment based on Newton's second law. So here's the real object. We have, as here we've got our, really hoping you can see my mouse. If you can't, pretend it's there. So we've got the time column here in the bottom right, and our x position column. As you see, as we increase the time, it goes further. It makes a lot of sense. We got this in the top right corner. We have this graph here. As you can see, we've got a downward sloping line. Now, a little sneak peek. You can see that graph. The slope of that graph starts to decrease a little bit. That's going to indicate some net force acting upon it, but we're going to get there. We're going to explain that more fully in a second. And then here's the GlowScript. So the GlowScript is how we made the computational model. It's pretty simple. Really nothing else matters besides delta t is our time step, and our ball position update. We updated it because we assumed in this model there were no forces acting on it. We just had to update we just had to update the ball position with how far it would go in this time step according to the speed we calculated. And then we use the time we calculated, or the average velocity of the object in the experiment, and then we made a computational model that lines up. So yeah, that's how we did that. And because there are no forces acting upon it, it's a very simple calculation or computation. All right, here's the meat of this lab. If you can see here, we've got our x versus t experimental and simulation. As you can see, this simulation model is a completely straight line, which indicates there are no net forces acting upon this object. Now, over here in the experimental category, you can see we start off with a slope that's steep, and then it starts to shallow off a little bit. That decrease in slope, and again, because the slope of the graph is the same thing as the velocity of the graph, we can see that the decrease in the slope is a decrease in velocity, and a decrease in velocity, going back to Newton's second law, means that there must have been some net force acting on the system from the more likely than not or net force acting on the system from the surroundings. Now, why do these two graphs disagree? Because there was a net force. Now, where did the net force come from? The surroundings. The most likely place for it to come from in the surroundings is friction with the table. That friction it's a force acting in the opposite direction of the movement. It opposes it, and it would slow it down. I guess air resistance could have been a little bit, but probably negligible. Then tracking errors. There could have been some tracking errors in Tracker that messed up our data, but I didn't really see any, and the data doesn't look like it has any, so I would assume that to be a negligible error. Additional questions. What if the axes were flipped? All you'd see is a negative graph, but the slope of the graph, it would be negated, but the absolute value of that would be the same. And then what were the actual net forces in the object? Were they actually zero? Because we saw that there was a decrease in velocity that we didn't predict in the computational model, we said there must be some net forces acting upon it in accordance with Newton's first and second law. So more likely than not, friction had a net force on it, and we didn't do anything to counteract it. So there was some net force loaded down. Okay, that's all. Thank you.